the beginning there was nothing. No stars to burn, no light to scatter, no time to measure its own passage, only silence. A silence so deep, it stretched beyond imagining. But even here, in the void before creation, the universe was not still. Beneath the surface of emptiness, something stirred. Modern science calls it the vacuum, but it is no hollow space. It breathes, it vibrates, it hums with invisible tension. Within this apparent nothingness lie restless fields, quantum seas where particles flicker into existence, only to vanish again before they can be seen. From this quiet turbulence, all things arise: the birth of energy, the curve of space-time, the glimmer of every galaxy. It is the paradox at the heart of reality, that everything we know is held together by what cannot be touched. The vacuum is not the absence of being, but the hidden architecture of it. Its invisible threads stretch across the cosmos, binding worlds that will never meet, shaping the rhythm of expansion itself. And somewhere within that unseen tension lies a force beyond comprehension, the pressure that keeps the void intact, the unseen glue of the universe. From the smallest quantum vibration to the farthest cluster of galaxies, it persists, subtle, eternal, silent, a cosmic heartbeat hidden beneath the stillness of nothing. In the dark fabric of space-time, between atoms, between stars, between every breath of creation, something holds the universe together. It cannot be seen. It cannot be measured easily. Yet it is there, the weight of nothing, the force that binds the void itself. And this is where the story begins, inside the silence, inside the vacuum, where nothing refuses to be empty. At the dawn of the 20th century, science stood on the edge of a quiet conviction. The universe, it was believed, was a stage built of absolute stillness, a vast, eternal void, cold and unchanging, through which matter drifted like lonely dust motes. Space was the nothing between somethings, a passive emptiness that simply was. For centuries, philosophers and physicists alike had trusted this vision. From Aristotle's concept of the ether to Newton's invisible grid of absolutes, emptiness was seen as a simple absence, the canvas upon which the universe had been painted. It was a convenient void, a perfect zero, untouched by motion or meaning. But then, in the faint glow of heated metal and flickering filaments, a small crack appeared in that ancient certainty. In 1900, Max Planck, working in a dark Berlin laboratory, tried to explain the strange colors of light emitted by hot bodies. The math refused to behave until he made an almost absurd assumption: that energy could not flow smoothly, but arrived in tiny, indivisible packets, quanta. That idea, microscopic bursts of energy, discrete and finite, would tear a hole through classical physics. It suggested that even the simplest wave of light was not continuous, not infinite, but granular, restless, uncertain. The universe, once thought to be smooth and silent, was beginning to shimmer with hidden activity. Then came Einstein. In 1905, his equations of relativity rewove the fabric of space and time, showing that gravity was not a pull between objects, but a bending of the very space-time between them. Emptiness was not passive after all. It could curve, stretch, ripple. The void itself was flexible, a living geometry that could respond to the presence of mass and energy. For the first time, nothing began to look suspiciously alive. By the 1920s, the revolution deepened. Heisenberg, Schrödinger, Dirac, names that would shape the quantum world, found that beneath the visible order of things, a strange uncertainty ruled. Particles could no longer be pinned to precise positions or times. They flickered in and out of being, guided by probability, not certainty. Heisenberg's uncertainty principle declared that one could never know both the position and momentum of a particle exactly. Reality, at its smallest scale, refused to be nailed down. It was as if the universe was built not on solid bricks of matter, but on a trembling haze of possibilities. From this haze, a new question emerged. If particles are never fully still, could the vacuum itself, that infinite space between them, ever be truly empty? The mathematics began to answer. In the hands of quantum theorists, the vacuum turned from silence into a kind of storm, a constant sea of fluctuating energy. Fields filled every point in space, vibrating at all frequencies, even when no particles were present. This was the birth of vacuum energy, not energy that comes from something, but energy that exists because there is space at all. Physicists realized that the quantum vacuum could never truly rest. Even when all known particles were removed, what remained was a wild ocean of invisible motion, particles appearing and annihilating in blinks of time too short to imagine. These virtual particles, as they came to be called, did not live long enough to be directly observed, but their presence left fingerprints. Their flickering gave rise to measurable effects, faint shifts in energy levels, subtle pressures between surfaces, deviations that could not be explained any other way. Einstein, meanwhile, had been wrestling with a different puzzle: the structure of the cosmos itself. His equations of general relativity implied that the universe should be either expanding or contracting. But the night sky seemed calm, its stars fixed in a steady geometry. To stabilize his equations, he introduced a new term, the cosmological constant, a kind of cosmic pressure that held space-time in balance. He imagined it as a property of the vacuum, a gentle repulsion countering the pull of gravity. It worked, mathematically at least, until a young astronomer named Edwin Hubble shattered the illusion. In 1929, Hubble revealed that distant galaxies were rushing away from one another, their light stretched into the red. The universe was expanding after all. Einstein, embarrassed by his earlier fix, called the cosmological constant his greatest mistake. But history would later show that the mistake was far from over. As physicists delved deeper into the vacuum, Einstein's discarded constant began to return, not as an error, but as a clue. In laboratories around the world, strange experiments began to reveal that even in controlled emptiness, forces were at play. The most haunting of these came in 1948 from two Dutch physicists, Hendrik Casimir and Dirk Polder. They placed two uncharged metal plates a few nanometers apart, inside what was thought to be a perfect vacuum. No air, no particles, no fields, nothing. Yet the plates moved. Slowly, silently, they were drawn together by a mysterious force. At first, it seemed absurd. How could empty space push anything? But the explanation lay in the quantum world's restless nature. Between the plates, certain wavelengths of virtual particles could not exist. The narrow space limited their fluctuations. Outside the plates, however, all wavelengths could thrive. The imbalance in vacuum pressure between the inside and outside caused the plates to attract. Space itself was pressing them together. This became known as the Casimir effect, and it was the first whisper that the vacuum, far from being empty, had structure, pressure, and presence. It was an effect so faint it could barely be measured, yet it spoke volumes. It suggested that what we call nothing was actually filled with the most subtle form of something, a sea of quantum activity, always shifting, always alive. In this revelation, emptiness lost its innocence. Quantum electrodynamics, or QED, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the mid-20th century, built upon this truth. Their equations treated every interaction between light and matter as the exchange of particles through fields that never truly vanished. Even the absence of particles carried potential energy. In this view, the vacuum was not a background, but a foundation, a fabric woven from quantum fields that could never be stilled. The electromagnetic field, the Higgs field, the gravitational field, all filled space, all restless. Every cubic centimeter of nothing contained more potential energy than all the matter it surrounded. Yet, paradoxically, this energy was invisible, silent, balanced against itself in near-perfect symmetry. The vacuum, then, was both infinite and fragile, a structure whose equilibrium allowed existence to persist. If disturbed, it could birth particles, radiation, or entire universes. And so, the question deepened. If nothing can exert a force, if emptiness can push and pull, what is the vacuum? Is it a medium, a field, a memory of the universe's creation, or is it a dynamic entity, a living backdrop that sustains the act of existence itself? The Casimir plates, closing their infinitesimal gap, seem to whisper of an ancient truth, that even when all else fades, the void remains awake. Every scientific advancement since that moment has been, in some way, an attempt to listen to that whisper. From the equations of quantum chromodynamics describing the vacuum of the strong nuclear force, to the discovery of the Higgs field in 2012, confirming that even mass itself is born from invisible energy fields. The story of the universe has become the story of nothing refusing to be nothing. The silence that once defined emptiness has been broken forever. Today, physicists describe the vacuum not as absence, but as a landscape of potential, a zero-point ocean from which all energy and matter emerge. Its properties determine the fate of the cosmos, the rate at which space expands, the stability of atoms, the flicker of radiation between stars. Nothing, it seems, holds everything. And though Einstein's cosmological constant was once abandoned, it remains an echo of this deeper mystery. The force that fills the void with quiet tension, the hidden pressure that shapes the motion of galaxies. What began as a question about stillness became a revelation about motion. The universe, in its most silent corners, is not empty at all. It hums, softly, invisibly, with the pulse of creation. The story of nothing had only just begun. At the dawn of the 20th century, science stood on the edge of a quiet conviction. The universe, it was believed, was a stage built of absolute stillness, a vast, eternal void, cold and unchanging, through which matter drifted like lonely dust motes. Space was the nothing between somethings, a passive emptiness that simply was. For centuries, philosophers and physicists alike had trusted this vision. From Aristotle's concept of the ether to Newton's invisible grid of absolutes, emptiness was seen as a simple absence, the canvas upon which the universe had been painted. It was a convenient void, a perfect zero, untouched by motion or meaning. But then, in the faint glow of heated metal and flickering filaments, a small crack appeared in that ancient certainty. In 1900, Max Planck, working in a dark Berlin laboratory, tried to explain the strange colors of light emitted by hot bodies. The math refused to behave until he made an almost absurd assumption, that energy could not flow smoothly, but arrived in tiny, indivisible packets, quanta. That idea, microscopic bursts of energy, discrete and finite, would tear a hole through classical physics. It suggested that even the simplest wave of light was not continuous, not infinite, but granular, restless, uncertain. The universe, once thought to be smooth and silent, was beginning to shimmer with hidden activity. Then came Einstein. In 1905, his equations of relativity rewove the fabric of space and time, showing that gravity was not a pull between objects, but a bending of the very space-time between them. Emptiness was not passive after all. It could curve, stretch, ripple. The void itself was flexible, a living geometry that could respond to the presence of mass and energy. For the first time, nothing began to look suspiciously alive. By the 1920s, the revolution deepened. Heisenberg, Schrödinger, Dirac, names that would shape the quantum world, found that beneath the visible order of things, a strange uncertainty ruled. Particles could no longer be pinned to precise positions or times. They flickered in and out of being, guided by probability, not certainty. Heisenberg's uncertainty principle declared that one could never know both the position and momentum of a particle exactly. Reality, at its smallest scale, refused to be nailed down. It was as if the universe was built not on solid bricks of matter, but on a trembling haze of possibilities. From this haze, a new question emerged. If particles are never fully still, could the vacuum itself, that infinite space between them, ever be truly empty? The mathematics began to answer. In the hands of quantum theorists, the vacuum turned from silence into a kind of storm, a constant sea of fluctuating energy. Fields filled every point in space, vibrating at all frequencies, even when no particles were present. This was the birth of vacuum energy, not energy that comes from something, but energy that exists because there is space at all. Physicists realized that the quantum vacuum could never truly rest. Even when all known particles were removed, what remained was a wild ocean of invisible motion, particles appearing and annihilating in blinks of time too short to imagine. These virtual particles, as they came to be called, did not live long enough to be directly observed, but their presence left fingerprints. Their flickering gave rise to measurable effects, faint shifts in energy levels, subtle pressures between surfaces, deviations that could not be explained any other way. Einstein, meanwhile, had been wrestling with a different puzzle: the structure of the cosmos itself. His equations of general relativity implied that the universe should be either expanding or contracting, but the night sky seemed calm, its stars fixed in a steady geometry. To stabilize his equations, he introduced a new term, the cosmological constant, a kind of cosmic pressure that held space-time in balance. He imagined it as a property of the vacuum, a gentle repulsion countering the pull of gravity. It worked, mathematically at least, until a young astronomer named Edwin Hubble shattered the illusion. In 1929, Hubble revealed that distant galaxies were rushing away from one another, their light stretched into the red. The universe was expanding after all. Einstein, embarrassed by his earlier fix, called the cosmological constant his greatest mistake. But history would later show that the mistake was far from over. As physicists delved deeper into the vacuum, Einstein's discarded constant began to return, not as an error, but as a clue. In laboratories around the world, strange experiments began to reveal that even in controlled emptiness, forces were at play. The most haunting of these came in 1948 from two Dutch physicists, Hendrik Casimir and Dirk Polder. They placed two uncharged metal plates a few nanometers apart, inside what was thought to be a perfect vacuum. No air, no particles, no fields, nothing. Yet the plates moved. Slowly, silently, they were drawn together by a mysterious force. At first, it seemed absurd. How could empty space push anything? But the explanation lay in the quantum world's restless nature. Between the plates, certain wavelengths of virtual particles could not exist. The narrow space limited their fluctuations. Outside the plates, however, all wavelengths could thrive. The imbalance in vacuum pressure between the inside and outside caused the plates to attract. Space itself was pressing them together. This became known as the Casimir effect, and it was the first whisper that the vacuum, far from being empty, had structure, pressure, and presence. It was an effect so faint it could barely be measured, yet it spoke volumes. It suggested that what we call nothing was actually filled with the most subtle form of something, a sea of quantum activity, always shifting, always alive. In this revelation, emptiness lost its innocence. Quantum electrodynamics, or QED, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the mid-20th century, built upon this truth. Their equations treated every interaction between light and matter as the exchange of particles through fields that never truly vanished. Even the absence of particles carried potential energy. In this view, the vacuum was not a background, but a foundation, a fabric woven from quantum fields that could never be stilled. The electromagnetic field, the Higgs field, the gravitational field, all filled space, all restless. Every cubic centimeter of nothing contained more potential energy than all the matter it surrounded. Yet, paradoxically, this energy was invisible, silent, balanced against itself in near-perfect symmetry. The vacuum, then, was both infinite and fragile, a structure whose equilibrium allowed existence to persist. If disturbed, it could birth particles, radiation, or entire universes. And so, the question deepened. If nothing can exert a force, if emptiness can push and pull, what is the vacuum? Is it a medium, a field, a memory of the universe's creation? Or is it a dynamic entity, a living backdrop that sustains the act of existence itself? The Casimir plates, closing their infinitesimal gap, seem to whisper of an ancient truth, that even when all else fades, the void remains awake. Every scientific advancement since that moment has been, in some way, an attempt to listen to that whisper. From the equations of quantum chromodynamics describing the vacuum of the strong nuclear force, to the discovery of the Higgs field in 2012, confirming that even mass itself is born from invisible energy fields. The story of the universe has become the story of nothing refusing to be nothing. The silence that once defined emptiness has been broken forever. Today, physicists describe the vacuum not as absence, but as a landscape of potential, a zero-point ocean from which all energy and matter emerge. Its properties determine the fate of the cosmos, the rate at which space expands, the stability of atoms, the flicker of radiation between stars. Nothing, it seems, holds everything. And though Einstein's cosmological constant was once abandoned, it remains an echo of this deeper mystery. The force that fills the void with quiet tension, the hidden pressure that shapes the motion of galaxies. What began as a question about stillness became a revelation about motion. The universe, in its most silent corners, is not empty at all. It hums, softly, invisibly, with the pulse of creation. The story of nothing had only just begun. For most of the 20th century, astronomers believed the universe was a patient thing. Expanding, yes, but gradually, as if time itself were stretching under a gentle pull. The galaxies drifted apart like embers cooling in the aftermath of the Big Bang. Gravity, the universe's great sculptor, was expected to slow this drift, to tug gently on the threads of creation, perhaps one day halting the expansion altogether. It was a comforting image, a cosmos that breathed in slow rhythm, bound by the familiar rules of attraction and decay. But in 1998, that quiet assumption broke. Far above Earth's atmosphere, where telescopes stared deep into the ocean of night, two teams of astronomers were searching for light from dying stars. Supernovae, those brilliant explosions that flare when massive stars reach their final breath. Type Ia supernovae, in particular, served as cosmic lighthouses. Their brightness was consistent, predictable. By comparing how bright they appeared to how bright they should have been, scientists could measure their distance across billions of light years. The plan was simple: chart the expansion of the universe with precision, test whether gravity was indeed slowing it down. But what they found defied everything. The supernovae were dimmer than expected, not because they were weaker, but because they were farther away than anyone imagined. Something was accelerating their retreat. Galaxies, instead of slowing under the weight of their own gravity, were racing apart faster and faster, as though the void itself were pushing them. In a universe ruled by attraction, this made no sense. There was no known force that could do such a thing. The data was rechecked, the calculations repeated, yet every observation confirmed the same impossible truth. The expansion of the universe was speeding up. The shock rippled through the halls of science. At the Lawrence Berkeley National Laboratory, Saul Perlmutter's team, the Supernova Cosmology Project, had reached the same conclusion as Brian Schmidt and Adam Rees's High-Z Supernova Search Team. Two independent groups, two separate telescopes, one shared revelation. The universe was not coasting towards silence, it was fleeing from itself. What could drive such a thing? What invisible pressure lived inside the dark? Physicists turned back to an old idea, one abandoned by its creator nearly a century earlier. When Albert Einstein first formulated his equations of general relativity, they suggested a strange truth. Gravity alone would cause the universe to collapse inward. To keep the cosmos static, as he then believed it must be, Einstein introduced an extra term, a mathematical counterforce he called the cosmological constant. When Edwin Hubble later discovered that the universe was expanding, Einstein discarded the constant, calling it his greatest blunder. But now, that forgotten term returned from the margins of theory, resurrected not by philosophy, but by necessity. To account for the accelerating cosmos, scientists revived Einstein's phantom. They gave it a new name, dark energy. It was the simplest yet most unsettling idea imaginable, that the very vacuum of space possessed energy of its own. That emptiness, rather than being void, was alive with invisible pressure, stretching space-time outward like a fabric under tension. If true, it meant that everything, every star, planet, atom, and field, existed inside a vast ocean of silent power. The implications were staggering. Dark energy was not rare or peripheral. It was the majority. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, mapped in exquisite detail by satellites like WMAP and Planck, confirmed that ordinary matter, the stuff of galaxies and life, made up less than 5% of the universe. Dark matter, the unseen scaffolding that holds galaxies together, accounted for roughly 27%, and the rest, nearly 70%, was dark energy. The nothing between stars was not empty, it was everything. Scientists could not yet see it, nor touch it, nor isolate it in the laboratory, but its fingerprints were written across the cosmos, in the accelerating drift of galaxies, in the geometry of space-time itself, in the whisper of ancient light still echoing through the microwave sky. To measure this acceleration, cosmologists turned to precision instruments orbiting high above Earth, telescopes like the Hubble Space Telescope, whose mirrored eye had already transformed the way humanity saw the heavens. By capturing the faint signatures of distant supernovae, they could trace how the expansion rate changed over billions of years, and what they found deepened the mystery. The acceleration had begun not at the dawn of time, but roughly 5 billion years ago, just when the gravitational attraction of matter began to weaken in the face of this new, invisible pressure. It was as if the universe had crossed a threshold, tipping from the dominion of gravity into the reign of the vacuum. In that transition, the cosmos changed its destiny. No longer bound to slow and contract, it was now destined to expand forever, its galaxies drifting into eternal separation, its stars fading one by one, until only darkness remained. The discovery forced cosmology to bend, not just its equations but its philosophy. If nothing contained everything, then the universe was stranger than imagination itself. Dark energy became the silent monarch of modern physics, dictating the shape and fate of all that exists. Yet its nature remained elusive. Was it a constant energy woven into the fabric of space-time, as Einstein once proposed, or something dynamic, a field that shifts and evolves, whispering through the quantum vacuum like a tide unseen? Every telescope, every detector, every equation turned toward the question, yet the answer slipped through like smoke. Some theories suggested a link to the energy of virtual particles, the restless foam of quantum fields that flicker in and out of existence within every cubic centimeter of space. Others proposed an entirely new essence, quintessence, a hypothetical fluid whose pressure drives cosmic expansion, and beyond even that lay wilder visions that dark energy might signal a multiverse, where each universe sprouts from the vacuum like a bubble in an infinite sea. But beneath all speculation, one fact endured. Something in the emptiness was pushing the universe apart. Even as scientists refined their measurements, the mystery deepened. The strength of dark energy, as inferred from observation, was many orders of magnitude smaller than what quantum theory predicted for the vacuum's energy. The numbers diverged so violently that physicists called it the worst theoretical prediction in the history of science. Somewhere, between the trembling equations of the quantum world and the sweeping geometry of relativity, the truth was hiding. And so, the discovery that began with dimming supernovae became one of the greatest riddles in human thought. In the years that followed, new missions were designed to chase the shadow. The Dark Energy Survey scanning distant galaxies from Chile's mountains, the Euclid Telescope and NASA's Nancy Grace Roman Space Telescope preparing to map the cosmic web in unprecedented clarity. Each sought to trace the fingerprints of this invisible force, to understand how it shaped the past and what it meant for the future. Because if dark energy continued its rule unchecked, it would not simply stretch the universe, it would define its end. In one possible future, expansion accelerates endlessly. Galaxies drift so far apart that their light never reaches each other again. Stars burn out, planets freeze, and the cosmos cools into eternal night. A heat death where entropy reigns and motion ceases. In another, Darker vision. If the pressure of dark energy grows stronger with time, space-time itself could rupture in a final catastrophe known as the Big Rip. Every atom, every quark, every trace of structure would be torn apart by the relentless expansion of the vacuum. Both futures, though opposite in violence, are born from the same source, the power of nothing. It is a force without face or form, yet it holds dominion over everything that exists. When the teams announced their findings in 1998, the world of science stood at a precipice, looking not into a frontier of stars, but into the mystery of the void itself. For the first time, physicists realized that the greatest force in the universe might not come from matter or radiation, but from the fabric of emptiness, from the whispering energy of the vacuum that surrounds all things. A Nobel Prize followed, awarded to Perlmutter, Schmidt, and Rees. Yet even as the accolades echoed, the sense of awe remained, a quiet recognition that the universe had revealed something profound, something humbling. The cosmos was not fading under the pull of its own gravity. It was running, faster and faster, into the darkness, and at the center of it all, invisible and unyielding, was the force that began as a blunder and became a revelation. The discovery that shook the universe was not about what was found, but about what could not be seen. A truth as silent as the void itself, a power that lived not in the stars, but in the space between them. In the vast stillness between galaxies, where matter thins into almost nothing, a quiet force endures, relentless, invisible, and impossibly consistent. It stretches across the cosmos like a ghostly wind, untouched by distance or time. Astronomers gave it a name, dark energy, but naming it did not mean knowing it. For in every equation, it disobeyed reason. Its most unsettling feature was not its power, but its steadiness. As the universe expanded, dark energy did not fade. The galaxies drifted farther apart. Space itself ballooned to scales beyond comprehension. Yet the energy of the vacuum remained the same, a constant density in a universe whose very volume was multiplying without limit. In classical physics, this was unthinkable. Energy should dilute as space grows. When a gas expands, its pressure drops, its heat spreads thin. But the vacuum, this strange sea of nothing, refused to behave. As more space appeared, more dark energy seemed to appear with it, as though the universe were conjuring it from nothingness to preserve the same invisible pressure. To many, it was as if the cosmos had broken its own laws. Physicists turned to quantum field theory, the most precise framework ever built to describe the subatomic world, to make sense of it. According to that theory, even empty space is not truly empty. It teems with restless activity, fields fluctuating, particles flickering into existence and vanishing again in less than a trillionth of a second. These quantum tremors, the so-called zero-point energy, were believed to give rise to the vacuum's energy. So, in principle, the mysterious dark energy might be nothing more than this quantum foam at work, stretched across the infinite fabric of the cosmos. But when the numbers were written down, the beauty of the idea collapsed into absurdity. Using known physics, the predicted energy of the vacuum, the cumulative energy of all quantum fluctuations, was colossal. Depending on the cutoff scale, the estimate came out around 10 to the power of 120 times larger than what astronomers observed through cosmic expansion. One followed the mathematics, and it led to a universe that should have exploded itself apart instantly after the Big Bang. Yet that did not happen. Reality, quiet and measured, refused to obey the calculation. This was not a minor error. It was the largest known discrepancy between theory and observation in all of science. It became known as the vacuum catastrophe, a name fitting for what it implied. Either a hidden symmetry was cancelling out nearly all of the vacuum's energy, or humanity's most successful theory, quantum field theory itself, was incomplete. For physicists, it was like staring at the blueprint of the universe and realizing one of its foundational numbers was wrong by a factor of a trillion, and more. Something was missing, something profound. When Einstein's equations are used to describe the universe, the cosmological constant, his once discarded term, fits neatly as a kind of pressure-pervading space. It does not clump, it does not thin, it simply is. Yet quantum theory, the engine of the microscopic world, suggests that this pressure should be enormous. Reconciling the two, the cosmic calm of relativity with the violent storm of the quantum vacuum, has become one of the greatest unsolved riddles in physics. At its core, this paradox asks a haunting question. If the vacuum is seething with invisible energy, why does gravity not respond to it? Every form of energy should warp space-time, as Einstein taught. The vacuum's energy, by that logic, should be the most dominant gravitational influence in existence. But in the universe we observe, its influence is gentle, barely perceptible, subtle enough that only the expansion of distant galaxies reveals its touch. Somewhere, a perfect balance must exist, a cosmic act of cancellation, a delicate tuning in which positive and negative contributions nearly erase one another, leaving behind the faint residue we call dark energy. But what could possibly perform such balancing on a cosmic scale? Some theorists suspect an undiscovered symmetry, a deep mathematical order, perhaps connected to supersymmetry, that forces the vacuum's energies to cancel out. Supersymmetry predicts that every particle has a hidden twin, a mirror partner whose contribution to the vacuum precisely offsets its counterparts. If this symmetry were perfect, the vacuum energy would vanish entirely. Yet in our universe, supersymmetry, if it exists, must be broken. The mirror twins, if they are real, are heavier than expected, their balance imperfect. The cancellation fails, but not completely. Enough of the vacuum's energy is neutralized to prevent cosmic destruction, yet enough remains to accelerate the universe. A coincidence so delicate that some physicists cannot accept it as mere chance. Others turn to more speculative terrain, the multiverse. If countless universes exist, each with different physical constants, then perhaps dark energy simply happens to be small here, by the sheer necessity of our existence. In universes where it was larger, galaxies would never have formed. Stars would never have lit. Observers would never have emerged to ask the question. It is a principle of cosmic selection, the anthropic principle, suggesting that the universe we see is not typical, but merely compatible with life. Yet this explanation, while elegant in logic, feels unsatisfying in spirit. It replaces understanding with survival, a whisper of, "It had to be this way," rather than, "This is why it is so." Meanwhile, the data remains stubborn. Measurements from the Planck satellite, the Dark Energy Survey, and baryon acoustic oscillations all point to the same truth. Dark energy behaves almost exactly like a cosmological constant. It does not appear to change with time. It does not flicker or wane. Its hand in cosmic expansion is steady, unblinking, relentless. This constancy deepens the enigma. For if dark energy truly arises from quantum fluctuations, why does it not fluctuate in turn? How does it remain uniform across the vastness of cosmic history, immune to the restless dance of particles within it? Perhaps, some suggest, dark energy is not an energy of the vacuum at all, but the effect of something else entirely. An emergent phenomenon, a property of space-time that arises only on large scales. Others invoke the idea of quintessence, a dynamic field that evolves slowly through time, mimicking a cosmological constant, but governed by its own hidden laws. Yet none of these ideas, however beautiful, has found proof. Dark energy remains the most precise mystery ever measured. A value known to extraordinary accuracy, but understood not at all. It is a force that should not exist, and yet it defines the universe. Even as galaxies drift apart, this invisible pressure keeps its rhythm. Even as time stretches and space grows colder, it hums beneath creation, unchanging. To imagine what it truly is, one must confront an unsettling possibility, that the laws of physics, so triumphant in describing matter and motion, may not yet touch the full nature of reality, that the frameworks built by Einstein and by quantum mechanics are fragments of a deeper unity not yet glimpsed. Somewhere, in the meeting point between the infinitely large and the infinitely small, the secret of dark energy waits, patient, silent, unbroken. Until that day, the paradox stands as a mirror to human understanding, the universe's way of whispering that the story of creation is not finished. In the vast emptiness where galaxies float, the force that should not exist continues its quiet rebellion, bending the fate of the cosmos while defying the rules that gave birth to it. And in that defiance, It reveals something profoundly humbling, that the deepest truths may lie not in what the universe contains, but in what it refuses to let go of. The vacuum is not empty. It is a balance too perfect to comprehend, a silence too powerful to measure, the force that binds nothing and yet moves everything. In the deep corridors of science, a quiet obsession began, to listen to the silence itself. The great instruments of the modern age, the machines built to pierce the heart of matter, turned their gaze toward what could not be seen. They were not listening for the crackle of cosmic explosions or the song of stars being born, but for something subtler, the faint, steady hum that pervades the void. For if the universe's expansion was driven by an invisible energy, then that energy must leave traces, faint ripples within the stillness. The task was nearly impossible, to detect the whisper of nothing. At CERN, beneath the fields of Switzerland and France, the Large Hadron Collider came alive. Its rings of superconducting magnets hurled protons to near light speed, colliding them in bursts of energy that mimicked the first moments after the Big Bang. To many, it was not just a search for particles, but an excavation of the vacuum itself, peeling away its layers like an onion made of pure energy. When the Higgs boson was found in 2012, it revealed a deep truth about the vacuum. The so-called Higgs field, filling all of space, was not merely an abstract idea. It was a physical entity, woven into the fabric of emptiness. Particles gained their mass not by inherent property, but through interaction with this invisible ocean that surrounded them. In that revelation, a quiet awe spread among physicists. The vacuum was not passive. It was alive. Even the emptiest regions of the cosmos were soaked in fields like the Higgs, unseen, omnipresent, endlessly vibrating. The same mechanism that endowed matter with weight also suggested that nothingness was full of structure. It had texture, resistance, and pressure. But this understanding only deepened the paradox. If the vacuum contained so much energy, why did it not tear space-time apart? Why did the expansion of the universe proceed gently instead of violently? The answers, if they existed, were buried within signals almost too faint to detect. Physicists turned their attention to the Casimir effect, one of the strangest laboratory manifestations of the vacuum's hidden life. Two uncharged metal plates placed a few nanometers apart in a vacuum experience a tiny but measurable attraction. No forces act between them, and yet space itself seems to push them together. The explanation lies in the sea of quantum fluctuations that fill the vacuum. Between the plates, only certain wavelengths of these fluctuations can exist. Outside them, all wavelengths are allowed. The imbalance creates pressure, nudging the plates closer. It is a force born entirely from absence, proof that emptiness has structure and that silence has motion. With each new experiment, the precision improved. Ultra-sensitive instruments measured the Casimir pressure with astonishing accuracy, sometimes differing by only a few femtonewtons. The data aligned with quantum predictions, confirming what theory had whispered for nearly a century. The vacuum breathes energy into everything. But while physicists in laboratories studied micrometers of emptiness, astronomers peered across billions of light years. The Planck satellite, launched by the European Space Agency in 2009, mapped the faint afterglow of the Big Bang, the cosmic microwave background. Its detectors captured the universe's oldest light, stretched by 13.8 billion years of expansion. Within that ancient radiation, tiny variations in temperature, no more than 1 part in 100,000, painted a portrait of the cosmos in its infancy. From these delicate imprints, scientists could measure the contents of the universe itself. Ordinary matter, the atoms of stars, gas, and dust, accounted for less than 5%. Dark matter contributed roughly 27%. And the rest, a staggering 68%, belonged to something unseen, dark energy. This was the whisper of the vacuum, recorded in the language of the cosmos. What appeared silent was, in truth, a constant dialogue between space and itself. Every cubic centimeter of the universe contained this pressure, invisible, uniform, and eternal. It governed the fate of galaxies, dictated the expansion of space-time, and shaped the horizon of cosmic destiny. In that realization, the line between experiment and philosophy began to blur. Scientists were no longer merely measuring physical forces, they were eavesdropping on the foundation of existence itself. Yet, the more they listened, the more perplexing the song became. At the smallest scales, quantum fields flickered chaotically, producing immense theoretical energies. At the largest scales, the universe drifted outward under a pressure that was almost impossibly mild. The bridge between those realms remained broken. At NASA, cosmologists used supernova observations, gravitational lensing surveys, and galaxy clustering data to test whether dark energy changed with time. Each new analysis returned the same haunting result. It didn't. The pressure remained constant, steady as the pulse of eternity. The vacuum's voice did not quiver or shift. It hummed, unwavering, from the birth of the universe to the present day. To test its constancy, new missions were planned. The Euclid Space Telescope, launched in 2023, began mapping the geometry of the universe in exquisite detail. Its goal, to trace how cosmic structures have evolved under the influence of dark energy. By measuring the shapes of galaxies and the bending of light, Euclid sought to map the invisible hand sculpting the universe's expansion. Further still, projects like the James Webb Space Telescope pushed into the infrared darkness, observing the earliest galaxies, frozen records of how expansion unfolded when the cosmos was still young. Each observation was another note in the symphony of the vacuum, echoing across billions of years. But for all the data gathered, the true origin of the force remained elusive. Some theorists speculated that vacuum energy was a property of space-time itself, an inherent tension woven into the cosmic fabric. Others proposed new fields, exotic fluids, or evolving forms of energy that could mimic a cosmological constant, while subtly changing over time. And yet, through all the speculation, one truth endured. The vacuum was not a stage for reality. It was reality. Everything else, galaxies, matter, light, was merely its momentary disturbance. To listen to the silence was to hear the foundation of existence vibrating just beyond perception. In laboratories cooled to near absolute zero, researchers continued their experiments, watching as vacuum fluctuations influenced atomic transitions, as light scattered from quantum noise, as energy appeared where none should be. Each finding chipped away at the illusion of emptiness. Meanwhile, across the black expanse, telescopes stared into cosmic voids, immense stretches of near nothing spanning hundreds of millions of light years. Even there, where galaxies were rare and darkness seemed absolute, the same expansion pressed outward. It was not the gravity of matter, but the breath of nothingness itself driving space to grow. To study this silence was to confront an idea older than science, that absence is not the opposite of presence, but its source. The vacuum's quiet persistence, its unwavering density, its universal reach, all of it suggested a hidden order, a rhythm beyond comprehension. If space is a field and time its flow, then perhaps the vacuum is the pulse, the steady heartbeat of the cosmos. Every atom, every photon, every life exists because this silence holds its shape, and so, scientists continue to listen, not with ears, but with equations, sensors, and the faint signals of collapsing stars and expanding space. Their instruments hum, their detectors cool, their data streams flicker across computer screens. Somewhere in those numbers, they hope, the silence will speak more clearly, but for now it remains patient, vast, unbroken, endlessly mysterious. Between every particle and every galaxy, the vacuum whispers the same refrain, that what appears empty is filled with creation's first breath, that nothingness itself may be the most eloquent form of existence. The universe, it seems, does not sing through stars alone, it sings through silence. In the vast stillness between galaxies, where light thins into memory and gravity begins to forget, the universe hides a secret more fragile than existence itself. It is the possibility that everything, every atom, every breath, every law of nature rests not upon firm foundations, but upon a trembling illusion. The vacuum, once thought to be eternal, may be temporary. This revelation emerged not from mythology or imagination, but from equations written in the language of quantum fields. Within those fields, the universe is not a quiet void, but a restless sea of probabilities, waves of energy rising and falling in endless uncertainty. From this sea, the Higgs field rises like a subtle tide, giving mass to the particles that build the visible world. It is this invisible ocean that allows stars to form, galaxies to coalesce, and life to exist. But buried deep within the mathematics of the Higgs field lies a haunting clue, a suggestion that our universe may not sit in its most stable state. Physicists call it the false vacuum. It is the idea that the vacuum, the very fabric of reality, might be perched in a shallow valley of energy rather than at the deepest point, like a ball resting in a dent along a hillside, stable for now, but not forever. A single quantum fluctuation, a whisper from the void itself, could send it rolling down into a deeper abyss. If that were to happen, the consequences would be beyond comprehension. In the mid-20th century, long before dark energy unsettled the cosmos, theorists began to explore how quantum fields shape reality. The equations revealed that even in perfect emptiness, energy never fully vanishes. Virtual particles rise and vanish within fractions of a second, lending the vacuum an invisible pressure. But when the Higgs boson was discovered in 2012 at CERN, its mass, roughly 125 giga-electron volts, revealed something unsettling. That number placed our universe at a precarious edge between stability and decay. The Standard Model, when extrapolated to extreme energies, whispered of a future where the Higgs field might slip into a lower energy state. Not today, not tomorrow, perhaps not for trillions of years. Yet the laws of probability do not care for comfort. They only care for possibility. Imagine a bubble forming within the vacuum, an infinitesimal region where the Higgs field drops into a deeper energy minimum. Inside that bubble, the laws of physics would rewrite themselves. The constants of nature, the charge of the electron, the strength of gravity, even the structure of atoms would shift into alien values. And then, with unstoppable speed, the bubble would expand. It would travel outward at the speed of light, converting everything it touched into this new vacuum. Galaxies would vanish before they even knew they were gone. No warning, no signal. Just silence, expanding. Physicists call this scenario vacuum decay. It is not a fantasy, nor a mythic apocalypse. It is a mathematically consistent possibility, a ghost hidden in the equations of the Standard Model. The universe, as it turns out, may be metastable, a temporary arrangement of energy that only appears eternal. At CERN, scientists continued to collide protons, probing deeper into the properties of the Higgs field. Each collision became a question whispered into the void. How secure is the reality we inhabit? Their instruments recorded the whispers of creation itself, particle tracks flickering across detectors like traces of forgotten lightning. But even with all their precision, the answer remained unsettlingly ambiguous. If the Higgs boson were slightly heavier, our vacuum would be stable, forever anchored. If slightly lighter, it would already have collapsed. The measured value sat hauntingly in between, as if the universe were balanced on the edge of a knife, its future undecided. Theorists turned to cosmology for guidance. They looked back toward the Big Bang, to the moments when the Higgs field first cooled and settled into its current state. During inflation, that mysterious burst of exponential expansion, quantum fluctuations rippled through space-time. Any one of those fluctuations could have pushed the universe from one vacuum state to another. That it did not is either luck or evidence of something deeper. Perhaps, some argue, there exists a hidden mechanism, a stabilizing symmetry or an unknown particle that anchors our vacuum in place. Supersymmetry once promised such salvation, but as experiments continued to find nothing, that hope began to fade. Others speculated that the instability itself may hold meaning, that universes unstable by nature might be the fertile ground for complexity, balance, and life. A kind of cosmic fine-tuning where the fragility of existence is not an error, but a design written into the mathematics of reality. If so, then our universe is a tightrope stretched across an abyss, and consciousness itself is the act of balancing upon it. But there is another question, darker still. What if the decay has already begun? If a bubble of true vacuum were to appear somewhere in the distant void, perhaps in a desolate corner of space, far beyond any galaxy, we would never see it coming. The expansion of space and the finite speed of light would ensure that by the time its boundary reached us, we would have already ceased to exist. This is the ultimate silence, not death, not destruction, but the total rewriting of what it means to exist. It would not matter what civilizations had risen or fallen, what stars had burned or been born. Everything, from quarks to nebulae, would dissolve into a new physics, a different kind of nothing. And yet, paradoxically, this terrifying idea reveals something profound about the universe itself. It means that even the void, even the nothingness between galaxies, is dynamic, alive with potential. It is not passive emptiness, but a cosmic field still evolving, still deciding what kind of reality it will host. Perhaps our universe is not decaying, but becoming. Perhaps vacuum instability is not a flaw, but a phase, part of the universe's own self-correction, a hidden logic unfolding across eons. Just as matter condenses from chaos, so too may order arise from instability. The boundary between a false vacuum and a true one may not be the end. It may be the bridge between universes. In the vast cosmological landscape described by string theory, there may exist countless vacua, each with its own laws, its own constants, its own kind of existence. If one collapses, another may rise. The death of one universe could be the birth of another. In this view, vacuum decay is not an apocalypse. It is genesis, repeated endlessly. But for now, our universe remains intact. Space continues to expand, galaxies drift further apart, and the cosmic background radiation fades like a dying ember. The Higgs field hums quietly, its fluctuations too small to trigger catastrophe. Still, the equations remain, cold, precise, and indifferent. They describe a cosmos poised between permanence and oblivion, between creation and collapse. A universe aware, in some mathematical sense, of its own instability. The physicist Joseph Likon once called it a universe with a built-in expiration date. And yet, that date, if it exists, is so distant, so unreachable, that it bends the meaning of time itself. In that sense, our fragility is also our eternity. To study vacuum decay is to confront an idea both terrifying and sublime, that the laws of nature are not absolute, but contingent, that everything familiar, from the beating of a heart to the orbit of galaxies, rests upon a cosmic coincidence that could, one day, shift. And still, existence goes on. Stars burn, atoms hold, life dreams. The vacuum remains quiet, for now. And in that quiet, there is a strange beauty, a reminder that the universe, even as it teeters on the edge of instability, continues to unfold, not as a fragile mistake, but as a fleeting miracle of balance. Because perhaps the greatest mystery is not that space-time could unravel, but that it hasn't yet. Beneath the visible world, beneath atoms, beneath light, beneath even the emptiness that separates the stars, lies a hidden ocean. It is not made of matter or energy as we know them, but of restless, unseen waves. These are the quantum fields, the silent architects of existence, weaving reality from the vibrations of nothing. To the human eye, the universe appears mostly empty. Between every atom, across the vast distances of space, there seems to be nothing at all. But modern physics tells a different story. One stranger, deeper, and infinitely more alive. Even when stripped of all matter, all radiation, and all light, the vacuum still hums. It is filled with quantum fields that cannot be turned off, cannot be erased, and cannot be silenced. They ripple with fluctuations, waves of potential that surge and fade within the smallest fractions of a second. The fields are everywhere. There is an electron field, filling all of space, a photon field, a Higgs field, a quark field, each one extending infinitely, overlapping perfectly, layered atop one another like invisible seas. Every particle that exists is not a solid object moving through emptiness. It is a local vibration, a ripple within these boundless fields. Matter is not something in space. Matter is space, structured by its own hidden music. In the 20th century, as physicists began to uncover the rules of the quantum world, they found that emptiness was far more complicated than anyone imagined. In 1947, two scientists, Hendrik Casimir and Dirk Polder, predicted a strange phenomenon. If two metal plates were placed extremely close together in a vacuum, they would attract each other, even though nothing visible lay between them. The force came not from magnetism or static electricity, but from the quantum vacuum itself, Between the plates, certain wavelengths of virtual particles could not exist, while outside them, the vacuum still seethed with its full storm of energy. The imbalance created immeasurable pressure, a push from nothing. When the experiment was carried out, the plates moved exactly as predicted. This became known as the Casimir effect, proof that the vacuum was not truly empty, but a dynamic sea of energy. Everywhere, invisible waves of electromagnetic fields were flickering into existence, creating virtual particles that paired and vanished almost instantly. These ghostly events happen constantly, their effects detectable in subtle ways. The shift in energy levels of hydrogen atoms, known as the Lamb shift, or the fine structure of light emitted by atoms, deviations that quantum electrodynamics could explain only by acknowledging the existence of these omnipresent fluctuations. In these details, nature whispered its secret. The universe is built from uncertainty itself. Quantum field theory took this idea further, describing reality not as a collection of particles, but as a grand tapestry of interacting fields. In this view, the electron is not a tiny sphere orbiting an atomic nucleus, but a ripple in the electron field. Light is not a stream of photons, but a vibration in the electromagnetic field. Every particle is simply the field excited in a particular way. When a photon strikes an electron, it is not two solid objects colliding, but two fields meeting in their oscillations, a handshake across the fabric of space-time. This framework, though abstract, became one of the most successful theories ever created. It predicted magnetic moments to 12 decimal places. It explained the spectrum of atoms, the behavior of forces, and even the existence of antimatter. It became the foundation for all modern physics, from the glow of a distant star to the machinery inside a smartphone. And yet, within this success lies an unanswered question. If the vacuum is filled with energy, why doesn't it dominate the universe? The equations of quantum field theory suggest that even when all particles are removed, each mode of every field retains a tiny amount of energy, the so-called zero-point energy. Summed across all frequencies, it should be immense, enough to curl space-time into oblivion. But the observable universe remains calm, its expansion gentle, its structure stable. The energy of the vacuum, somehow, is either cancelled or hidden. This mystery connects the quantum world to the cosmic one. It hints that the same fields responsible for the Casimir effect and the Lamb shift may also drive the vast, dark energy that pushes galaxies apart. The invisible architects that shape atoms may also shape the fate of the cosmos. Between the smallest scales and the largest, between quantum mechanics and cosmology, the vacuum stretches like a bridge. The same silence that hums beneath an atom may also whisper at the edge of the universe. In laboratories on Earth, scientists have begun to listen more closely to that silence. At CERN, particle accelerators probe the quantum fields directly, smashing protons together to reveal the patterns of energy that lie beneath. When two protons collide, their fields overlap and vibrate with such intensity that the vacuum itself briefly destabilizes. Out of that storm, new particles emerge, not conjured from matter, but from energy condensed into form. This is creation at the smallest scale, a glimpse of how the universe may have once emerged from its own vacuum. Elsewhere, in the cold chambers of precision experiments, physicists measure the Casimir effect with astonishing accuracy, detecting pressures between plates thinner than a hair and separated by nanometers. Each tiny force they observe is a fingerprint of the quantum vacuum, the soft pressure of reality itself breathing in and out. The Lamb shift, measured with lasers tuned to impossible precision, reveals how these fluctuations subtly alter the structure of hydrogen. The equations of quantum electrodynamics, refined by minds like Feynman, Schwinger, and Tominaga, describe this dance with unparalleled accuracy. Every result, every observation, leads to the same conclusion. There is no such thing as nothing. The vacuum, though silent, is busy, and yet for all our understanding, the origin of these fields remains a riddle. Why do they exist at all? Why do their constants take the values they do? Why does the Higgs field, in particular, endow some particles with mass while leaving others untouched? The answers lie hidden in the same mystery that gave rise to dark energy and space-time itself. Some physicists suspect that the quantum fields may not be fundamental, but emergent, like waves upon a deeper ocean we cannot yet perceive. Others propose that the fields are woven from the geometry of space-time, that space and time themselves are quantum objects, flickering in and out of being. If that is true, then the universe is not built upon space. It is space, vibrating with the memory of creation. The Higgs field offers a glimpse of how such invisible forces sculpt reality. It permeates all of space, uniform and silent, yet through its gentle resistance, it gives particles their mass. Without it, there would be no atoms, no chemistry, no stars. The Higgs is not a force in the traditional sense. It is a background, a texture in the vacuum that shapes how everything else behaves. In 2012, when the Higgs boson was detected, it was like hearing the faint resonance of that background, a ripple moving through the invisible sea that underpins reality. In that moment, the world saw the quantum vacuum not as a void, but as a creative medium, a field capable of sculpting the universe itself. Even now, theories continue to deepen. Some suggest that quantum fields might not be continuous, but granular, that space-time itself might emerge from entangled networks of information. Others imagine the vacuum as a holographic projection of deeper, hidden dimensions. Whatever the truth, one theme persists. Reality is not built on emptiness. It is built from it. The universe is a conversation between silence and motion, between nothing and something. Quantum fields are that dialogue, constant, invisible, eternal. They are the unseen architects that breathe form into void, that write particles into being, that dissolve them back into possibility. Every second, across every corner of the cosmos, they rise and vanish, composing the world from the ghostly music of probability. And so, the story of existence becomes a story of vibration. From the hum of electrons to the glow of stars, from the faint pressure between Casimir plates to the expansion of the universe, all of it begins in the same ocean, the restless fields that never sleep. Perhaps the ancients were not entirely wrong to imagine creation as sound, as a word spoken into the void. In the equations of physics, that word is vibration, and its echo is everything that has ever been. In the quiet depths of reality, the architects still work, invisible, tireless and eternal, shaping, unshaping, reshaping all that will ever be.